All right, guys, so we start with number 9, and it's dealing with exponential growth and exponential decay based on our equation y equals a times b to the x power. Okay, where a is our initial value, that's what we start with. So starting value, also known as our y-intercept. So whatever your a value is, that's where it's going to cross the y-axis. And then your b value, that's your exponential growth / decay, depending on if you're increasing or decreasing. So the first question, number 9, says the function y equals 85 times 1.2 to the x represents the number of bunnies in Central Park x years after 2000. Is this an example of exponential growth or decay? And then the next question says, how many bunnies will there be in 2010? All right, so first thing we have to answer is either growth or decay. So my a value won't help me here, but we can go ahead and start talking about that. That 85 there, that's my starting value or my y-intercept. So if I was graphing this, it would cross the y-axis at 85. It also tells me my starting value, my very first value that I would have is going to be 85. So I start with 85 bunnies. Next, to see if I have exponential growth or decay, I need to be looking at my b value, which is this one. And this is the one that we're really focusing on. So this 1.12. Anything that's bigger than 1 is going to be an exponential growth. Anything smaller than 1 is going to be an exponential decay. So here my answer is going to be growth. Next it asks me how many bunnies will there be in 2010. The equation that they give me is for x years after 2000. So at x equals 1, this will be 2001. At x equals 2, it'll be 2002, so forth and so on. So what I do is I go to y equals. I type in my equation, which is 85 parentheses 1.12 to the x power. Then I go to my table, and again, they're asking me at 2010, which this is x years after 2000. So at 10, that's also the same as 2010. So my answer here is going to be 264 bunnies. So that's my solution. For number 10, again, very similar. It says a person is taking a prescribed drug from his doctor and has y equals 125 times 0.75 to the x remaining in his bloodstream after x hours. Is this an exponential growth or decay? About how much will remain in the system after 5 hours? So again, he's taking a drug from his doctor, a prescribed drug. And so this is how much he originally starts with. So that's his starting value. This is how fast he's either growing or decaying. Remember that if it's anything smaller than 1, it's going to be a decay. So here 0.75 is smaller than 1, so we have a decay, which is usually what happens when you have prescription drugs in your bloodstream, is that they start off at a high amount and then your body slowly starts fighting them off, and so they start decaying. Their effects start to decay over time. And so this is going to be a decay. And then what happens after 5 hours? Again, I just simply go to my calculator and I type this in. So we have y equals, this time we have 125.75 to the x. I can go into my table, and this time we're looking at just 5 hours afterwards, so it's going to be 29.663. That's how much is left in my bloodstream after 5 hours. All right, number 11. The value of a certain stock is represented by the function f, where x represents the number of days since the stock was purchased. Look at the table. Which exponential regression is used to determine the function for this data? All right, so a few different ways to do this, and I've actually seen a few of my students do it this way. So some of my students have actually gone in and done stat edit, which you're more than welcome to do. You can type in your values and you actually get very close to the solution. But another thing that you can actually do is you can actually go in and you can look at your equation. You can more or less narrow it down. And then it's just basically going to be a table match. If you type these into your y equals, one of those will match this table exactly. So 2 different ways to do it. Again, if you want to do stat edit, you can. but let me show you guys how you would do it the other way. So to do it the other way, basically you want to first cross off any that don't make any sense. So for example, my equations, if I start looking at my values, if I start looking at what I start with, now these say 10 and these say 0.95. I really don't start with 0.95, I start with 9.5. But if I started at 0, what do I start with? That's the question. And so it looks like it would be 10. It's definitely not going to be 0.95, just because we go 9.5 and then 9.0 something, right? So we're in the 9s, not in the 0.9s. So we can more or less cancel this one out. The other reason we cancel this one out is because this has a 10 as our change, which means that we would be multiplying by 10 each time, which if we look at our numbers, they're not growing by 10 each time. It's not like we're going 9.5 and then 90 and then 900, then 9,000, right? We're not doing that. So we can go ahead and cross off A. Next, if we look at our Y values, not really just looking at our changes, just basically not really doing this, but just basically asking ourselves, as my X values increase, are our numbers getting bigger or are they getting smaller? In other words, do we have a growth or do we have a decay? Now here I start with 9.5. By the end of the table that it shows me, I'm at 8.1, right? So I'm decreasing in value, so we have a decay. So next I want to go through and I just want to make sure that I choose values that are decaying. This one is 0.095. That's definitely smaller than 1, so this one's in the running. Y equals 10.95, so my change here is times 0.95, which again is smaller than 1, so that's a decay. However, D says 10 parentheses 1.05. 1.05 is bigger than 1, which would be a growth, and we definitely don't have a growth in our table, so I can also cross off D. All right, so I cross off those two. Now I'm between B and C. So now what I do is I just type these into my calculator and check to see which one of these gives me my table. So 10 parentheses 0.095 to the X, go second graph, figure out my table. So if my table is correct at 1, I should have 9.5, and this one gives me 0.95, which is not right, and then 0. So it's all off by just a slight amount. Just to make sure, I want to type in the other one. My other expression is 10.95 to the X. So if I go to my calculator and I hit table, this one says 9.5, 9.025, 8.5, 838, 8.1451. So this one matches my table perfectly. So my answer here is going to be C. Like I said, you could have also done stat edit, and if you didn't want to do all the, maybe if this part of me crossing off the A and crossing off D confused you, just understand that you could have also typed those in as well. I was just showing you guys a different, like a brainstorming way to cancel some of those out. All right, number 12 says, what is the stock after 12 days? So here, the equation was to measure stock. So now that I've found the equation, now that it's in my calculator, I can actually go to day 12 and figure out how much it's going to be worth. So on day 12, it's going to be worth 5. And again, this is money, so we kind of have to round up. This is going to be worth $5.40 after 12 days. Number 13, it says, if a population of 300 increases by 3% every year, how large will the population be in 10 years? So this is the one that I really wanted to explain so that we all understand exactly how to do this. So population, we start with 300. And once again, we're using our equation. Hopefully we know this by now. Y equals A, B to the X power. Right, so A represents my starting value, so I know that I'm starting with 300, so we have Y equals 300. I'm going to go ahead and leave my B blank for now. I'm going to say to the X power. Now, I want you guys to think, just because this percentage always throws students off. Okay, so I want you guys to think. And let me just give you guys an example. In one of my classes, I have 22 students. Okay? So whenever I go in and I take roll, if I go in and I count all of my students and I have 22 of them, that means that I have 22 students and I go in and I count and I have 22 of those students there that day, that means that all of my students are here. What I would say is that I have 100% of my students in class that day. Right? So think about this the exact same way. If 300 is our starting value, and at that particular time I have all 300 show up, that means that I have 100%. Right? So always make sure that you start with 100%. Your equation always starts with 100%. From there, you either increase or decrease based on your value, right? So this one says that we have an increase of 3% every year. So I'm going to go ahead and add 3% to my already 100%, and I'm going to get 103%. Okay, so I started with 100%, I increased by 3%, and now I'm at 103%, which always, for whatever reason, throws students off just because they say, how can I have 103%? And the answer to that is, that's why we call it a growth. We call it a growth because you start or you end with more than what you originally had. You end with a surplus of 3%, which is why you have a growth or an increase of 3%. All right, now the only problem with working it this way is that if I put 103 or 100 plus 3 in here, that means that I'm multiplying by something close to 100, right? And that's not what I want to do. Anytime that we have percent, just understand that the key word or the key phrase of percent is if you break down that word percent, that means part of 100. So what you really have to do to change percents into decimals is you have to go in and divide all of these by 100. So you go in, divide all these by 100. 100 divided by 100 is going to give you 1. 3% divided by 100, which again you can do on here, is going to give you 0.03. So plus 0.03 is going to give you 1.03. Now, what goes in here is completely up to you, or you just have to know how to interpret both. Sometimes they'll write it in this way, the 100% plus the 3%, also written as 1 plus 0.03, or they'll write it this way, 1.03, which again, you have to understand that both of these things are equal. Both of these things really mean the same thing. So it's completely up to you what you want to write in here. But that's going to be my equation. Now I just want to point out one other thing before we actually work the rest of this problem and we look at 10 years into it. I just want to show you guys a different way that I think about this. Anytime that I think about percents, I usually think about money, and it makes sense. And so let me explain it to you guys this way. The 100%, that's like you always starting with $1. Okay, so whenever you think about this problems like this, instead think, okay, I start with $1. If I increase by 3%, again, change percents in your head, just change them and make them cents. So I increase by 3 cents. Well, if I have $1 and I add 3 cents to it, that's 3 pennies. So now I'm at $1.03. And this is what I would put in there. Again, obviously without the money sign or anything like that, but that's what goes in there. And then so now, if I give you guys any number, you can tell me if it's a growth or a decay, and you can also tell me what percent we're growing by, again, if you think about it like money. So again, if I give you guys a number like this, 1.17, and I ask you guys growth or decay, hopefully we can all say growth, and we can all say growth by 17%. Simply because if I think again, $1, I start with $1, I have 17 cents extra on top of that dollar, that's going to be a growth of 17 cents. And we're actually going to go back and talk about a problem like this. So for example, this one, which is 0.75, we already said it was a decay. Again, if we think back to our scenario of we start with $1, how much did I lose to get to 75 cents? I lost 25 cents. Right? So since I lost those 25 cents, I can say confidently I have a decay of 25%. Right, so we can also think about it in these terms, and it can help you with that. All right, flipping it over to the back, we're going to go ahead and finish this up. So the back, problem number 14 says an exponential function contains ordered pairs as shown on the table on the right. What is the rate of growth for the function? So again, the key word here is rate of growth. How fast is this thing growing? The way that we do that is we have to go in and we have to check our delta y, check to see how much this thing is jumping. Now again, understand that this is not going to be linear, again, because we have a rate of growth, which means that we should be multiplying one thing times one thing times one thing times one thing to jump from one to the other. Right, which we can also tell there's nothing that I can add. I can't add 8 plus something to get 40 and then add the same thing to get to 200. That just isn't going to work. To figure out your ratio, the thing that goes out here, you always do your second number divided by your first. So my second number here is 40. I'm going to divide that by my first number, which is 8. So 40 divided by 8 is going to give me 5. Okay, once I have that 5, that tells me that my rate is going to be 5. I'm multiplying by 5 each time. Again, that's what this helps you do. So 40 divided by 8 gives me 5, which then you would have to go in and check to make sure that all of these are multiplied by 5. Which again, you just check in your calculator really quick. 8 times 5 gives you 40. Check. Then if we do the next one, 40 times 5 should give you 200. And then I'm just going to check the last ones just for fun. 200 times 5, 1,000, and then 1,000 times 5, 5,000. Right, so all of these work, which means that my ratio here is 5. Or in other words, my rate of growth is 5. All right, last few. So this one says a graph. This graph represents an exponential function that has an initial value of 10. So we start at 10 and has a rate of decay of 1/2. Use this graph when answering the following questions. So based on this graph, which again, you're more than welcome to graph it if you want on your own calculator. But based on this graph, we're thinking about how to solve the next 3 questions. So the first question says, what is the domain of the function? So again, the thing that we have to understand here is that domain stands for x values. So what we're going to do is we're going to be looking at just our x values using our x-axis to measure this. So domain means x values, so we're going to be using this to measure our function. So what do I mean by measuring our function this way? That means that you want to look for where it starts on the left side and where it ends on the right side. That's what we're trying to do. Now these arrows here at the end of our function mean that that function is going to keep going. So really this graph, even though it's not really angled this way, I'm just going to exaggerate it a little bit. Eventually this graph is going to go this way. Right, and again I'm exaggerating it just because I don't have enough space to really draw out this line, but just eventually it will, over time, curve that way. Right, so since this is at enough of an angle, it will, I can't say, well, it stops here. I can't really say that because that arrow means that it keeps going. And then it keeps going. And then it keeps going. Right? So that is just going to keep constantly going left and left and left and left and left, which means that it's going to go all the way to negative infinity. Right? And on the right, it's a little bit easier to see. It's going to actually do the exact same thing on the right. It's going to go this way and keep on extending this way forever. Again, because the arrow means that it just keeps going and keeps going and keeps going. Right, so it's going to keep on extending that way. That means that it's also going to reach another infinity, and this time it's going to be a positive infinity. So it's going to reach all the way over here, and then all the way over here. So it's going to reach every single number in between. Anytime that our line spans from one infinity to the other, we can write that as all real numbers, which is also written as this little thing, which again means, I'll shorthand the numbers. It means all real numbers. My range. So your range obviously is very, very similar to your domain, but in this case, your range, this means y values. So now we're going to be measuring the same equation, but this time we're going to be using our other axis. So now we're using this, our y-axis, to measure our line. So now we're measuring our line using this. Now, we measure our range from bottom to top, so now we're looking at that same line, but we're looking at what's the lowest point that it reaches and what's the highest point that it reaches. Now, here's where it can get a little tricky, simply because, if I could find my pen, is where it gets a little bit tricky, because this line, this x-axis, if I were to extend it just a little bit further, okay, that's my x-axis. If I were to extend this line just a little bit further, they get really, really close to each other. So this line gets really, really close to each other. In fact, what's happening is all of my values keep getting cut in half. So again, we start with 10. 10 gets cut in half. We get to 5. 5 gets cut in half. We get to 2.5. 2.5 gets cut in half. We get to 1.25. And then that gets cut in half, right? And so further and further and further and further. So these things just constantly keep getting cut in half. But mathematically, what that means is that if these values keep getting smaller and smaller and smaller and smaller, as long as you have something and you cut it in half, you will never get to 0. Right? So these values will never, ever, ever cross this line and go into the negatives. They will never do that. They're going to stay and they're going to hover right above 0 forever. So all of my values will never, ever, ever equal 0. They're always going to be above 0. And then this line, of course, is going to shoot up towards the top. This one's going to go all the way to positive infinity. Right? So we have 0 to positive infinity. The way that we would write that mathematically is just going to be all y values greater than 0. So any y value you can think of, any number you can think of bigger than 0, this line is going to cover, but it's never going to cover in any negatives. It's never going to go dip below that 0. The last one, number 17, it says, what is the asymptote of the function? Now, this is a fancy vocabulary word that we learned at some point, or you should have learned at some point with your teacher. And so asymptote, all that means is just an imaginary line that your graph is never, ever, ever going to cross. Okay? So again, that imaginary line right here is going to be this line right here, which we're going to go ahead and write two names for. So that imaginary line there, we're going to go ahead and write, technically, again, I said it's not equal to 0. So our line, our actual equation itself is never going to equal 0. But the line here, the asymptote, is going to be the line that it never crosses, which is going to be that exact thing, y equals 0. So it's never actually going to cross 0. And this is where I think the calculator really comes in handy. Again, I just want to show you guys what this means. So again, I'm going to use the information up here and type in my equation, which is going to be 10, 1/2 to the x. And again, that should give me the graph that's on here, more or less. So that graph should match this. So now if we go to our table, we can even see our values. So at 0, we have 10, and then it keeps getting cut in half. 5, 2.5, 1.25, right, so forth and so on. If I start scrolling down, and this e to the negative 7 just means that it's a really, really small number. Right? Just because your calculator can't fit that many zeros in there, it starts doing this little e thing. But you see our numbers get smaller and smaller and smaller and smaller, and even though we can't really read those or understand those very clearly, we know that it's smaller and smaller and smaller and smaller and smaller. And so no matter how far we go, it's just going to get smaller and smaller and smaller, but it's never going to actually equal 0. So the line that it approaches but never actually touches is going to be that line exactly, y equals 0. We can also write this, so I'm going to go ahead and say or, we can also write this a different way, because this line here also has a different name, and that name is going to be the x-axis. So just understand that sometimes the STAR test likes to use y equals 0, sometimes it likes to use the x-axis. You have to be able to understand that both of these mean the exact same thing. They mean this line right here, which is never going to touch. And in fact, most of the time, in fact, I think like 99% of the time, it's going to be one of these two. I can't really think of a graph in algebra where this would happen somewhere around like 4 or something else. It usually is going to happen at y equals 0. All right, so that was your review. Hopefully it made sense to you. And if you guys have any questions, of course, ask your teachers before you take your test. So immediately after, come in with your review and ask any questions if you need to. As always, have a good day, and hopefully I made this a little bit more clear to you guys, and hopefully you guys study for your test. Good luck on your test tomorrow.